module. So as we would normally do, we will do a quick recap of what we have discussed earlier. Actually, after that, Professor ISG also in a way somewhat discussed some of these, that this is the overall compilation phases, compilation flow of the C program, with the preprocessor removing all directives and expanding things into a .i source file of C code. And then when the compilation happens into the assembly, and then assembler takes over, then the linker and so on. Then we started looking into inside of the compiler, which is after pre-processing, we have a pure C program source as a translation unit, which is lexically analyzed to group characters into lexical tokens or meaningful symbols of the language, whether it is predefined symbols like operators or keywords, or they are symbols of identifier names that are created by the user. So lexical analyzer does that grouping, and then the parser checks if according to that grouping the grammar is correct, and they interoperate, coordinate between them, keeping the symbols in a table called symbol table. And once the parser structure is ready, it is interpreted to generate the code, then the code optimized, and so on. So this is the overall process we are talking of. We took a look at this overall flow, starting from the character stream to token, then the syntax tree, then the annotation of the syntax tree with the semantics or meaning, representation in an intermediate form, and optimization, and final code generation. So this is the example we looked at, a very usual, typical assignment expression, where we have grouped characters, scanning them from left to right according to the lexical rules which are specified by the design of the language. And we discussed that this is the point where the rule of identifier or the rule of floating point constant or the rule of integer constant, all these are used, or the list of operators or the list of keywords. This particular example does not have a keyword, but the different operators. And then it is transformed from left to right in terms of token classes, and if required, the specific token marker. Like Fahrenheit is identified, so the token class is ID. And we have a marker 1 to say that it is a first identifier. Centigrade later on is identified as another token, which is an ID class, but it is a second token of the ID class, so it is marked as 2. And possibly in a table like symbol table, we'll have these entered in a certain way. Others are, these are special symbols like operator, assignment operator, multiplication operator, addition operator. These are marked as separate token classes. Similarly, we have token class floating point constant and the actual value 1.8. So here I would again like to reiterate that when we write it in the pro code, it is like a character string. So 1.8 is actually a string of character symbol 1 followed by character symbol dot followed by character symbol 8. But when we have lexically analyzed and grouped them together, we say that according to the rules of floating point constant, we have found a grouping of this string 1.8, 1 period 8, which we call the lexem of this token. For this lexem 1.8, we have identified that the token class is floating point f constant, and 1.8 is the value that we convert the string into. So when we write 1.8 here, we are actually meaning the value, not the character string. So now when you actually write down in terms of, for our own understanding, for human understanding, they look the same. But this actually, the one on top is actually the string of characters, and one below is actually the representation of the value, which will expand out within the lexical analyzer as a binary string. Similar thing will happen for this character string 32, which will be recognized as an integer constant and the corresponding value 32. So this is the first basic step that we saw. We saw different variants of a very similar assignment expressions here, which can be processed exactly in the same way by the lexical analyzer to produce the stream of tokens, which go as input to the syntax analyzer. And then we tried to look at these assignment expressions in parallel and tried to look at them in the next group as token symbols. All of these F, B, V, all these are IDs, identifiers. So I said their structure is identifier, assigned identifier times 1.8 is a number, 32 is a number as well. So these are all variants of a very similar type of assignment expression, which going to the third stage in terms of syntax is basically saying that each one of them fall into really one category, which is expression times expression plus expression assigned to expression. So this first line is E assigned E star E plus E is the basic rule or the grammar according to which all these three different lexically different assignment expressions are formed. It's not only that, we also see that there is something more to that, because in this whole assignment expression, there are three operators. One is a multiplication operator. If we start from left, there is an assignment operator, there is a multiplication operator, and there is an addition operator. Since there are three operators, there is question of the order in which you let the operators actually operate on the expression and produce results which are used subsequently in the other operators. This is what you all know as the precedence order. So according to the precedence order of these three operators, multiplication has highest precedence, followed by addition, and finally assignment has the lowest precedence. So what we see in terms of the grammatical structure of this assignment expression with parenthesis actually tells us as to in which order this will happen. So this is from starting from the character string going through the lexical tokens. This is the representation in terms of the grammar is what we are looking at the syntax analysis level. So this is where the syntax analyzer comes in. It takes the output of the lexical analyzer, as you can see the stream of tokens. And then this whole information, if I go back to the previous slide, if I come back here, this whole information of which operator happens first and which happens next is actually represented very well in terms of a tree structure. So here, through the syntax analyzer, we are extracting, interpreting more information from the program stream, which is a stream of tokens now, and converting the one-dimensional list into a two-dimensional tree structure, wherein how is that tree structure given us more information? In this tree structure, the basic idea is every node is an expression. So either it could be an elementary expression like an identifier, it could be an elementary expression like a literal, floating point constant literal, or integer constant literal, or it could be an expression which is computed out of two expressions. It could be one expression also, it could be three expressions also, but in general, very typically we will use expressions that are binary. So these are operators which will operate on two expressions and will generate a third expression which has a value. So naturally, how does this tree work? Obviously, anything which is at the leaf level is an expression by itself. It's a primitive, so it has a value. And naturally, any node, internal node, which has the value of both its child expressions can be computed, and the value of that node can be found. So if we look into this tree, we can very easily see that at the beginning, only this operator star is what can actually operate, because that is the only operator node which has both its expression, child expressions ID and 1.8, which are primitive, and therefore they can be computed by this multiplication to generate the result. So in this tree, it becomes very unique, unambiguous, that this multiplication has to happen first. Once that has happened, then this
Sir, you are not audible.
So not audible, sir.
Yes, I have informed him, PPT. He is reconnecting.
ISG, can you hear me now?
Yes, yes.
I had to go out and come in. I don't know what's going on. Is it visible and am I audible?
Fine.
Yeah. So we discussed about treatment of this node. So this obviously is the first operator which has to work. Now, once this has worked, then between these two, the operator assignment has this ID available. This expression is available because it's a primitive expression. But operator plus has not happened yet. So this value is not known. Therefore, this cannot happen. The assignment cannot happen. But if we look at plus, then its right operand is a primitive expression, which is integer literal. It's available. And star, we have seen the multiplication has already happened between these two. So this is also available. So this operator becomes available for evaluation. And then once this addition is done, we have a value, which then the third operator can work. So you can see that the advantage of, I'm going back one slide. So this is the generic form of the expression that we had, E assigned E star E plus E. And we needed a couple of parentheses to say what is to do first and what is to do next. You can see that when we come to this kind of a tree structure, tree expression, then that precedence order, and as we'll see that same thing will happen if we have associativity playing a role. That is, if there are multiple operators of the same type occurring side by side, where associativity becomes important. We'll see that that ordering gets resolved if we represent in this kind of a tree structure. So that will be very typical, that's a syntax analysis. We'll follow certain rules, we'll say the grammar rules or the parsing rules, which will convert the linear string from the output of lexical analyzer and generate this two-dimensional syntax tree, which has only one unique way to interpret in terms of the computation. So this is what we had seen earlier. Now, once we have that, then the question is, can we really go ahead and evaluate? Well, we know the order in which they can be evaluated, but can we really evaluate at the level of values? So what we see is, again, if we just revisit the evaluation, we are first doing a multiplication, and we are doing a multiplication with 1.8. What is 1.8? It is the floating point constant. So what we expect, suppose if our ID has a value 4, then the multiplication with 1.8 will produce 7.2. So we expect that the value represented at this node multiply operator, this star node, is something which is a floating point value. Whereas what we have here on the right operand of the plus node, addition node, is an integer value, is an integer constant. And as you would be aware, and in any case, as Professor ISG was explaining, that in the organization, in the processes, typically you have separate addition modules for doing integer addition or for doing floating point addition. So the question is, if one value is floating point, which is here, and other is integer, what type of addition do you do? So the choice is to convert one into the other. Normally, we will do the conversion in a direction so that you do not lose information. So instead, we will, instead of thinking of 32 as an integer, we would rather think of it as a floating point number 32.0, and then do then compute a floating point addition between the product created here 7.2 and the value converted value 32.0 to generate 39.2. So as you can see that before this plus can actually happen, which is what we thought should happen next, actually this conversion of 32 to 32.0 has to happen. So to represent that, we introduce another node here. And this you can see is another operator node, but this is a unary operator node. Unlike the other ones which are binary, because here it takes only one operand and produces the result. That one operand is an integer value. It takes that and generates a floating point value. And as you would be aware that this is not as trivial as we write out in our script in the decimal, that we just put a period and put a 0, because typically the representation of the integer constants or integer numbers and the representation of the floating point numbers are very, very different in the system. Integer is actually expanded out in terms of its binary representation with certain way to maintain the sign. So there are various forms of sign number representation and all that, which you may have done. If you have not done, you will do it in your COA course. And on the contrast, a floating point constant is not like a whole number and a fractional part. It actually is represented in some form of a characteristic mantissa form, and has a very, very different way to write out the same number. So 32 and 32.0 are not at all easily convertible representation in binary. So you need to have an operator. You need to run, any operator is an algorithm. Just remember this. Right? What is an operator? An operator is nothing but a function. Because it takes an input, gives you an output. So it's like a function, it's like an algorithm. So into float is also like an algorithm, like a unary operator, which takes 32 in terms of its integer representation and produces 32.0 in terms of a floating point representation. And then the plus operator has both of them, which are floating point. Then the addition can happen and then the floating point assignment can happen. So in this whole of the process, what is on top of the syntax has not changed. The order in which you do things are not changing. What operand applies is available for which operator is not changing. So the syntax is same, but the semantics, the meaning has changed. The actual, what you mean by a particular node or what you mean by a particular computation had to change, for example, in this case, to allow for a mixed mode addition. So that is typically what the syntax analyzer will do. It takes the syntax tree and creates certain modifications on it, maybe gets that edited and changed. And we often call that as an annotated syntax tree, wherein it actually comes closer to what the programmer means in terms of the program. So this is what we have now got in terms of the original expression. So now you see that what we wanted to do, you wanted to create a compiler. That is, starting from the C program, we actually want to create an assembly language program, as Professor ISG was showing you day before yesterday, that the GCC minus S and all creates an assembly language program. So, but have we got that? We haven't really been there. What we have got is we have been able to create an intermediate representation, an internal representation for the input C expression in terms of a tree. So wherein if the values are given, then we know how to do the operations and actually generate the result. That we have got. But this still is not this is a kind of a data structure, not a program in an assembly language or anything of that sort. So now our attempt would be that can we, instead of actually representing it in the form of a tree, can we actually write it out in terms of a very elementary set of program expressions? That is, the idea is that if I'm multiplying ID2 by 1.8 and getting a result here, so this is an expression which is a product of ID2 and 1.8. Can I give it a name and have a temporary variable which stores that value? So I'll say, okay, given this, I give it a name T1, temporary one. What is temporary one? It is the product of ID2 and 1.8. If that be the case, then I can take 32, operate with this operator and generate another value, which again I can keep in a temporary variable. I can give it a name, say T2. T2 is into float of 32. If we do that, then this plus is nothing but, this addition is nothing but T1 plus T2. So kind of what I'm trying to tell you is we can, as we have taken the whole expression, done a lexical analysis, syntax analysis, put the semantics, we can again put it in the form of a very, very rudimentary program structure, where what I'm just allowing is take the operands, do a binary or unary operation, generate a result, give it a name, use that name again. So that is the next stage that we are going to do. And that is what is called the intermediate code generation. I'm showing it here for a little bit more generic expression than this. I'm showing it here for A assigned B star C plus D. First, let us try to understand the syntax tree. What does it mean? This is, as you can see, it's the syntax tree. So here, the only difference that we have done, I'm saying it is a syntax tree, but there's a little bit of difference that we have done. What is the difference that we have done? Here we have, in the earlier tree, we were directly connecting the expression values with the operators. Here instead, we are using some generic symbols, auxiliary symbols. symbol E. What does E mean? E means some expression. So any node which is E has a value. That's it. So what do you say? E is an identifier B. ID is identifier. So E is an identifier B. So B as an identifier has a value. So this represents that the node E has a value which is B. And that value is represented as, say, E dot result. Just a rough choice. Similarly, I can say that C is an identifier, and this node E has a value of C. So E dot result is C. Then we say, what is this node? This node is a product of these two expressions. This node E is the product of the left-hand side expression E and the right-hand side expression E. Product is a basic operator. So the left expression on left is V, left expression on right is C. So this is actually B star C, or the product of B and C. And let us give it a name. So this did not exist. This B times C is being computed. It did not exist. So we give it a temporary name, say T1. So I call it, this is T1. So I say if I do this, then expression identifier B is the value of this expression. Identifier C becomes the value of this expression. And this expression is a product of B and C because it's a product of these two expressions. And I give it a name T1. So I can say that E dot result, the value of this expression is T1. So I proceed in that manner. I get identifier D, which is the value of this expression. E dot result is D. And then what is the expression on top? It is expression on left, whose value is T1. An expression on right, whose value is D. And those two are getting added. So it is T1 plus T. And I again give it a temporary name as T2. So T2 is T1 plus T. That is the value of this expression. Then we say that finally I will do the assignment. I'll assign this expression T2 that I have got into an identifier A through this assignment operator. So I have A assigned T2. So you can see that if I do this, then I will eventually have, let me just stop sharing and show this to you in little bit more detailed stuff, little bit to work out. Just give me a minute. I think you can see it again. So what we did is T1 gets B star C. So this is this is my original input. A assigned B star C plus D. And what I'm produced is T1 getting B star C, T2 getting T1 plus B, and then finally A getting T2. Right. So you can see that, oh, I have to again go back. Let me share it differently. I see, is it visible? I see.
Yes, it is visible.
Yeah,
Yes,
yeah.
yes.
So
Yes.
this is what we are seeing in terms of the tree. We have BC multiplied to get T1, D added to that to get T2, and T assigned here. So what it necessarily means is in terms of this particular expression in C, which has three operators at the same time, is now broken down into smaller expressions or smaller statements where each one has only one, at most one operator. But it does compute the same thing. So this is a kind of a conversion that we are achieving at this point, which makes our life a lot more simple to deal with, because however complex my original expression could have been, here at every stage I'm just taking two values and doing one operation, or I'm just taking one value and doing one operation, or I'm not doing any operation at all, just making an assignment. So from the syntax tree, from the annotated syntax tree, we convert the program into this kind of a representation, which is called an intermediate code representation. So things like this are said to be the intermediate code, which are often referred to as three address code or quad code. Why is it three address code? Because if you look at each one of them, you have at most three addresses to deal with. Like this first one, T1 is computed from B times C. So you have three addresses, the address of B, address of C, and the address of T1. The second one is three address code because you have again three addresses, T1, D, and T2. The third one is called three address, but it has only two addresses, T2 and A. So the three address code is one where, see, if you are using binary operator, then it is the three addresses that you need in the maximum, because binary operator means you have two operands and you have one result. So three addresses is what you need. So using a three address coding scheme, you can take any expression whatsoever in C, or for that matter in any language, and actually convert them in terms of a series of three address expressions. So this is also referred to as kind of a quad code. It's called a quad code because to remember this whole expression, this whole three address code or this particular code, you need to remember four components. The four components are three, you already know, are the three addresses. And the fourth one is the operator that is involved. So to be able to write this, I need to know that the first operand is B, second operand is C, result is T1, and my operator is star. So if I know these four, I know this whole code. So this is also called a quad. Quad means four, quad code representation. See, the beauty of this is when I have brought it in terms of this kind of a linear program back. So again, if I think back, we started with a character stream, then we converted it to a token stream, then we got into a two-dimensional syntax tree, then we had semantics annotated on that, and then we are converting back into a sequence of instructions, with the beauty that these instructions are now very, very simple. They are all three address instruction or quad instructions, and are kind of independent, are kind of being done in a way so that all issues of precedence of operators, associativity of operators, everything is already taken care of. So once that is generated, so I'm back to the original example. This is the semantic tree that we had generated from our centigrade to Fahrenheit converter. And now we go through that intermediate code generation process. So first we do multiply these two, ID 2 times 1.8, generates this node, which is T1. Then I have to do this. We have already explained 32 converted to the 32.0 by into float. That is my T2. That is at this point, the output of this. Now these two have to get added. So T1 and T2 have to get added. T1 plus T2 is T3. And then T3 gets assigned to ID1. So T3 gets assigned to ID1. So this whole syntax tree, annotated syntax tree now gets converted to a intermediate sequence of codes. Okay. So this is what we have got so far. And we can see that, well, if we look at this code and start thinking, you would say, okay, there are a few things which we are doing unnecessarily. Because what we will do, to be able to actually do the conversion, I'll have to specify ID2, which is the temperature value in centigrade. It will go through all this computation to give me ID1, which is the equivalent temperature value in Fahrenheit. Good. Now, if we look at each and every 4 of these quads, then I can easily see that this second quad, which is T2 getting into float 32, is independent of my input. It's a constant operation because conversion of 32 into float is independent of any other value. So why do we compute it every time? We could compute it once and just remember. And that's what is a basic flavor of optimization. So I can compute and remember that. And if I remember that, then do I need to put it into T2 or I can directly put it into the value T2 here? If I do that, I have optimized the code. So I got this. I had to do this. Then I convert this 32 into float assigned to T2. This becomes 32.0. Then I can replace this 32.0 into here. So it becomes T1 plus 32.0. Now we see T1 plus 32.0 is assigned to T3 and then T3 is assigned to ID1. So T3 actually has no special role. I'm copying into T3 and then I'm copying from T3. So I can cut short that. I can just make it. So I get finally this code, which is ID2 times 1.8 gets assigned to T2 and T1, and then T1 is added with 32.0, which gets ID1. So you can see that now I am doing actually exactly as I will do by hand. If I'm given to do it by hand, is I'll take the value of the centigrade, multiply it by 1.8, add 32 to it, and that's the result. So in this whole process, I have not only converted it to a representation of quad, but I have also been able to optimize it and get an optimized representation. So this was about kind of the front end of the compiler. So at this point, let me stop and check if you are following me before I proceed with the back end and further details. So I will just stop and ask if you have questions. You can put your questions on the chat or raise the hand. Yeah.
Sir, my question is like, suppose there is an operation like multiplication of
dear, whenever you ask a question, please identify yourself. That will make it more human.
Sir, I'm Shubham. Shubham Mission 18 CS 1
Yes, Shubham.
So my question is, suppose there are two constants like say 32 and 54, and somehow I am in my code I am multiplying them.
Right.
So when intermediate code generation happens, so it will be like you will write like the quad code as T1 equals to multiplication of those constants, right? But when code optimization takes place, so what will be optimized? Like those two multiplication operation, that multiplication operation will remain, or it will be multiplied beforehand and stored.
You can see that I mean, I'll not take such complicated numbers. Suppose it happens that there's an expression called 3 times 5. Right? Now, naturally, in the intermediate code, I will generate, say, some T1 assigned 3 times 5.
Yes.
But then I will argue that 3 times 5 does not change on anything else in life. So I can compute them at the compile time itself. I do not need to compute them every time I run the program.
Okay.
So that process, as we'll see, we'll come to study about all possible such things that can be done. It's called constant folding. So instead, what I'll do, I will make this as 15.
Okay.
3 times 5, I'll make it 15. And the interesting thing could be that when I do this, my next step could be T1 is added with 4. Now, if I have known that T1 is a constant 15, then T1 plus 4 will now become folded as 19.
Okay.
Right? So it can have a, ripple effect.
Okay.
It could actually lead to several. And several cases, this kind of a constant folding has a severe advantage. I'll give you a very typical thing that we do, which use this significantly in C programming. Suppose you want the value of pi. In a program, you are computing area of a circle, circumference of a circle, so you need the value of pi. Now, how do you get the value of pi? Value of pi is not easy because it's a transcendental number. So what will you write? 3.14? There is error. 3.1425. So how many decimal places you will write? So all those questions are there. So it is very common in programming. You may have seen this. Is you compute the value of pi from the arctan function. You know that tan inverse 1.0 is pi by 4. So value of pi is 4 times arctan 1.0. Right? Now, this whole expression will need a lot of computation because arctan function cannot be computed directly. It is an infinite series, so it will go through several iterations. And then the value at which it will converge is the value of pi by 4, which will again multiply by 4 to get the value of pi. Huge computation. But you will argue that it is arctan of 1.0, so that's not going to change. So at compile time, I can actually compute this arctan 1.0 multiplied by 4 and store that as my value of pi for the whole program.
Okay.
So as many times I may have used pi, I save my computation.
Okay.
So that's the constant folding. I mean, there are optimization is a big area, and we will try to do quite a bit of that. But these are all different ideas that can be used, which actually make our program fast enough for the real purpose. Okay, Shivam.
Okay, sir. Thank you, sir.
Welcome. Any other question?
Somnath is having a question on the chat box.
Yes.
Somnath Jena is having...
Somnath Jena, you are saying then all operations involving constant are computed at compile time. Not involving constant, all operations which are constant expression. So obviously, x times 5 cannot be computed at compile time because x is not known. But any expression whose all arguments are constant can be computed at compile time. So that is the process which is called constant folding. Okay, that's very interesting. I'm moving on to the next question, Srihash. How are loops represented in the syntax tree? See, syntax tree is the way the program. How do you write it in the program? How did you write in the loop in the program? Let me take this question on the graphics. Let me show you how, at least one simple example of how you can do this. So I've shared. I think you can see this. Right.
Yes.
So let us see what is a loop. Let me write a loop in C. A loop in C is while. Okay. Say A less than B. Okay. And then you have something like x x assigned x plus 1, something. I say something like this. Now, if you look at this, then what will you have? Say if I just draw out, so I'll say this is while. While, what is while? While in terms of our language, while is a keyword. Okay? So I need to remember that this is a keyword which exists. Then what do I have? I have a opening parenthesis. I'm just following. I'm just following what is written there in the text. There's a closing parenthesis. Then I have do. So these are the 4 things I have in a while loop. And in the middle, what I'll have? I'll have that binary expression, right? That Boolean expression. So here, what do we have? I have an expression. So I can say that what is a while loop? While loop is a statement S which has multiple different node child, which makes the while loop. Finally, I'll have one which is the body, which is this part, for which again I'll have a, for this I will again have a syntax tree. So according to my syntax tree, I say that a statement, a loop statement is while followed by opening brace, followed by an expression, followed by a closing brace, followed by do, followed by a body. Now, if you are not happy with seeing an expression here, I will say, okay, don't worry. I'll say that this expression is nothing but a less than b, which is this. You say, where is my a and b? I said, don't worry, I'll put this up. I'll say this is, this expression E is A, and this expression E is B. I mean, I'm assuming that you can think about the links properly between them. That is, an expression here is expression here is basically E less than E. Similarly, an expression here is expression E is here is A, and so on, right? So this is how we represent the whole of this loop structure. And this body is, again, what is the body? The body is another statement. So body is like another S. This could be another loop by itself. It could be a set of curly brace. Within the curly brace, it could be a sequence of instructions. Right? So that's how we will follow the structure of the language, of the statements, and be able to represent loops and so on. Mind you, this is syntax tree is not a flow chart. It is not a control flow diagram. It's not showing you the control. It is showing a representation of the program that we write in terms of tokens, which are not just the characters, but the groups that they mean. So I wrote the whole of while as one unit, the whole of do as one unit, because those are the keywords that are represented. Srihas did it. It was a little long answer, but I hope it explained to you at a basic level.
Devojyoti had a similar question with for loop.
Yeah, I mean the budget you can see that this whole thing. I can just for the sake of it. I don't think I'll do more examples like that, because we certainly will do a lot of these later on. But just since it is coming to your mind, so I will say S is a statement which is for opening brace, expression, brace. I'll say an expression is something which is expression. I'll say expression is something which is expression less than expression. In this, I'm sorry. So just think about, just try to map for onto this kind of a structure, and it will come in. Is this whole for starting from here to here? This whole stuff is a statement. So I'm saying it's a statement. What is a statement? It's something which starts with for as a keyword, has an opening parenthesis. Then it has three expressions: the first expression, the condition expression, and the tail expression. So this expression. And then you have what follows the for, another single statement. So you have another S, because it could be exactly the same or some other statement. And then I'm saying that what are these expressions? These are different types of expressions that you have written. Here you have written an initialization expression. Here you have written a comparison expression. Here you have written a unary operator, post operator, E. So all sorts of different expressions that you can have. So in this way, I have not shown you the earlier parts, but in this way, these are basically what are called the grammar rules, according to which the syntax is specified. That is what we have learned while we have learned the C program. These are the rules were told to us. Like what is for? For is it will have for, then three expression. This expression will happen once. This will be the condition check, and then it will have a single statement following. So when we learned about that specification of for, we learned two things. One is we learned the structure, that it starts with for, has three expressions, separated by semicolon, followed by a single statement. This is the structural part, which is a syntax tree. Then we learned the semantics, the meaning, which said that when the for control comes to for, expression one is evaluated irrespective of anything else. Once that is done, then expression 2 is evaluated, and if that turns out to be true, then we proceed in the for. If it turns out to be false, we jump over. These are all meaning, these are all semantics. So that is what will the semantics analyzer do by annotating on the syntax tree. And then we learned that if this expression, the second expression, is true, then I'll go to the body of the for loop, which is a statement by itself. We'll do whole of that body and come back to the third expression, the tail expression, complete that and come back to the second expression. So this whole rule we studied in C program. Why did we study that? Where does it play the role? This is where it will play the role. The first is telling us the structure, which gives me the syntax tree in terms of the grammar. Second set of rules will give me the semantics of what will happen when I actually execute a for statement. So I'm making representations for that. These are all we will detail out. I'm just trying to tell you the phases of the different significant components of the compiler that it will work. And as you will see later on, that they are not separated out in the actual compiler. I mean, I'm presenting them as separate so that we can understand. And as we go ahead and we learn more and more, we'll see that all of them will get amalgamated into a big chunk, which is the front end. Right, I think we have had, there's no further questions right now. So let me just go back and try to finish this discussion. Let me again. I hope this is feasible now. Okay.
Yes.
So this is what we have got in terms of the front end. I'm yet to explain to you, justify why I'm using this term front end. I'll justify that after I have actually discussed the back end. So this is a part of the translation that you have used, understood. Now there is still a big gap between what Professor ISG told in the class day before yesterday, showing you what happens when you do, some main.c minus w all minus s, or GCC minus w all minus s main.c kind of stuff. We are still not at the assembly language. So the next task would be to actually take this intermediate representation, the 3 address code representation, and convert that into the assembly language. So that is what the backend would try to do. So before continuing with that example, I'll just show you a little bit of a hypothetical example of what kind of different optimization that can happen. I'm just taking a little bit more complicated expression, a plus b star c plus d. Now, as you can see, how many operators are there? 3 operators, plus, star, and plus. So actually 2 operators, 3 instances. Now naturally precedence, star has a highest precedence, so this multiplication will happen first. Then this becomes a value. Then you have 2 operations, 2 pluses. So between the 2 pluses, plus has a left associativity. So the left one will happen. So this will happen first, this will happen second, this will happen third. Clear. So now what if you write it down in a longhand expression, then you have I'm just assuming that every expression gets a name, named temporary. So T0, T1, T2, A, B, C. Then this multiplication happened because you are processing it from left to right. So A is kept in T0, B is kept in.
But PPT, one observation.
Yes.
There are 2 additions, A plus something plus D. So here in computers, addition is not associative, because A plus the first one, that might result in overflow, and D might be a negative number. So if I do the second addition first, there will be no overflow and we'll get the correct result.
That's absolutely right, ISG.
Yes.
But that will be kind of in the beginning of November. Those things would be at the beginning of November, because now we are just doing the baseline rules.
Yes.
So the baseline rules will have only one order. When we do the final optimization stage in the back end, at times we make these choices that whether changing this order might actually give you something which is better in terms of computation. We need this associativity order to be specified, otherwise the syntax tree cannot be formed. So we need either it to be left associative or right associative. It cannot be both. So for that matter, we are using left associative. That is what I'm meaning. Okay. So what you are saying in terms of computation will be handled, may be handled at the optimization level. Okay. So Now, if you look at this left one, then you have A, B, C, T0, T1, T2. And this structure you must have understood very well, the three addresses. So T1 times T2 is T3, which is because certainly this has higher precedence, so this will get computed. Then this addition happens. So T0 plus T3 is this addition, which is A plus B star C is T4. Then I get D as T5, add T4, T5, I get T6. Right. So if we just generate the code in a very native way, that every expression has a temporary to store the value, then this is what we'll get. Now, if we pass through this more, we can see that, well, there are places where things, so many temporaries need not be used, and I can optimize by using less number of them. For example, T0, T1, T2, all three need to be remembered at the same time. Right? I mean, I cannot put A to T0 and B to T1 and use T0 or T1 to keep C, because I need to remember all three of them together. But think about this step. T3 gets T1 plus T2, T1 times T2. Now, after this has happened, if you look in the later part of the program, how you do that is a second question. Do not get worried about how we will get there, but just do the observation here. That from this point onward, if you look at the rest of the program, there is T1 is never used. So once the value of T1 has been used in computing T1 times T2 and putting it T3, I can actually do not need the value of T1. So I can reuse that. So what I do, instead of doing a new temporary T3, I reuse T1. So T3 is not required because I can reuse T1. So I do this. I have done that. I come to the next one, then I make a very similar observation. T4 is T0 plus T3, and T0 is not subsequently used. So I can reuse T0 here. So I use T0 here. T0. Then I come to D taking as T5. Okay, I observe that T is taken as T5. And if you see the T1, which is used here, which is defined here, is used at the subsequent one because T1 actually replaced T3. So it has replaced T3 at this point. So this is T1. But beyond that, it is not used. So I can again reuse T1 to mean something else. Its value that was computed has already been used. So instead of T5, I can use T1 and replace this T5 by T1. The whole code rewritten. T4 has already become T0. So this is T0. T6, not required. So T0 is not used anymore. I can use T0. So you can see the same logic is rewritten, but instead of 6 temporary, now you need only 3 temporary. T0, T1, T2. Would you be happy with that? Let's take another look. Let's say here I'm doing T2 is C. So I can, and T2 is used here and not used anywhere later on. So I can simply replace T2 by C. I can replace T2 by C. And I don't lose anything. By replacing T2 by C, I get exactly the same thing, and I can make use of doing this. And subsequently, I can see that actually, all in the later part, I do not need separately D to be stored in T1 because I can replace it right here. So this goes in 1, 2, 3, 4, 5, 6, 7 instructions, now become 5 instructions. So that's the basic flavor of different types of optimization. Now, how we do it, what kind of analysis goes in, how you do it in general. You have to make sure that after optimization, you do not make a mistake. The code must remain correct and all that. But this is what typically goes on, and you can practice more of that as you go forward. Okay. So this is just for your information. This is the kind of things that happen. We will do data flow and control flow analysis. We'll have to see how does the control actually goes from one point to the other, which data has already been computed, which needs to be computed. And then finally, we have to, finally, we have to come to the next step, because recall what Professor ISG all through discussed, or those percentage RAX and all that. You did not see any name of a temporary variable. In fact, you did not even see the name of a variable. All of that were replaced by two things. One is either by registers or by address expressions. You saw the EBP and offset from EBP. Right? Because that is how the assembler has to map the variables onto the physical addresses where they're stored. So that is the next step that gets to happen. So I'm skipping over a huge lot of details at this point, which we will have to discuss, but just trying to show you how this can happen in terms of these two. So what I need to do is to actually do this multiplication. Now, to be able to do this multiplication, this value ID2, which I'm writing as ID2, will show up in your assembly language in terms of an offset expression. You know, some EBP percentage minus something, etc. Right? Which is what I'm representing. Now, I take that and store it in a register. This is some, this is not any specific assembly language, this is some abstract assembly language, you can say. So it's a load instruction, which is loading the value of the identifier ID2 into register R2. R2 is a register. So this becomes R2, then I can do this multiplication. And what kind of multiplication I have to do? I have to do a floating. This F means floating point. So I do a floating point multiplication of this value with 1.8, this value with 1.8. And after multiplication, I do not need ID2 anymore. See, I'm trying to do something which I could not have done so far as I was dealing with the identifier itself. But now that I have copied that identifier into the register, I'm arguing that the register R2, which has a value of ID2, after the multiplication with 1.8 has happened, I don't need that value anymore because ID2 is not needed any further. So I can use that same register to store my result. So I use the same register to store my result. So I do R2 times 1.8 and do not store the result in R1 or R3. I store the result in R2 itself. So which means now what was the result? The result was T1. So whatever is now become R2 does not anymore represent ID2, but it actually represents T1 because that is the result computed. So when that is used to add with 32.0, this T1 is nothing but R2. So I again use R2. I have 32.0 to add to. After addition, I will generate a result. And again, since T1 is not needed after this, R2 does not need to be preserved. So the value of R2, which was T1, after addition with 32.0, I can forget that. And the result of T1 plus 32.0 is again placed in R2. So this whole expression is now R2. It's a floating point addition that I've done. Finally, I need to assign this to the identifier because that is the user-defined identifier where I want the result. So I store R2 into ID1, which is where ID1 itself will again be another expression of the offset kind. So here, all that I had to do in terms of a temporary T1, I actually manage all of that in terms of a register R2. And what you get is an equivalent assembly language translation of the code. And at this point, you would be you would start getting the insight as to why did I did we design the tree address code or the intermediate code in this quad form, because you'll see that most of these quads have a structure which is very, very close to the typical assembly language instruction, which also have actually implement binary operators. So they have two operands and a result. Or they have an address and a value to go to, like jump less equal to, you have an address. Right? So all of these are very easily mappable from one tree address code to one or more assembly instructions. And that is the final thing that we get. So if we just go through the overall thing that we have done, so we have started with this kind of an expression. I've just to get out of the boredom of converting centigrade into Fahrenheit, I've taken the positional constant speed. So you have a rate at which you are going. This is the time, then the initial position, then the final position. So we do the lexicon analysis, we get this identifier stream coming in. We do the syntax analysis, we get this syntax tree. This comes first because the highest precedence, then the addition, then the assignment. We do the semantic analysis and we get into float on 60, possibly because identifier ID1, ID2 or ID3, these are floating point identifiers. So I get this, then I put them, converting them back into generating the intermediate code. So I first generate code for this, which is into T1, multiply it by ID3, which gets me T2, add ID2, which add that with ID2, which gets me T3, and assign T3 to ID1. Then optimize it in the tree address. And if I optimize, I'll get this is constant folded and then propagated here. So I get ID3 times 60.0, that is out of these two expressions, these two tree address codes. And in this, T3 can be easily propagated in. So ID1 is ID2 plus T1. And then I convert it by taking this value, multiplying it by 60.0, storing the result in the same register, then proceeding, then taking on ID2 in another register, and then adding these two registers into the register of ID2 itself, R1, and put it back to the ID1, the original. So this is a typical flow of the compiler of the different phases, and all that we will study throughout the semester and all that we will develop throughout the laboratory would be starting from here, which is a character-based textual description of the program, to converting into an assembly language, which is what we have specified. So for us, this will be a subset of C, which is tiny c, and this will be x86 language, as Professor ISG has already explained. Having said that, let me tell you that what is the significance of front end and back end. So we'll say that somewhere here, somewhere around here, the front end ends, and somewhere around, and remaining part of it is back end. Why do we need these separation? You can see that this is a compiler is a translator. It is taking from one language, translating into another language. I think somebody's microphone has got unmuted. Okay, can you have it muted, please? Yeah, okay, thank you. So a translator is from a source language to a target language. The source language is kind of C here, target language is x86. Now, if you see, if you start from this phase and come on to here, if you go through this part, you'll see these modules, these phases that we pass through here are dependent on the source language, the language that we are translating from. For example, what will be the lexical items? That depends on the specification of C. What is the kind of operators, what is the kind of constructs we have, that depends on C. What is the meaning that we have for different construct depends on C. So these are components which are significantly dependent on the source language. Whereas when you go to this end, as to finally, I have translated it onto x86 processor. That naturally depends on the assembly language of it, its addressing modes, its register structure, its interrupt mechanism, all of that. It depends on the target processor that I'm targeting. Now, naturally, we want a translation mechanism so that some n languages can be translated onto m different processors. That is, I can have a C compiler for Intel x86, I can have a C compiler for Mac, I can have C compiler for so many different 32-bit, for 64-bit, a variety of different target machines. Similarly, for x86 processor itself, I could want to write a C compiler, a C++ compiler, a Java compiler, a Python compiler, and so on and so forth. So both of my input source language and my target language can vary, and that's what the compilers I need for. Now, if I had to write a single piece of the compiler, then the number of compilers I will need would be m source languages and n target languages will mean that I have m times n different compilers to write, which starts from one language and ends up in a target language. That's a huge infeasible task. So what we do, we are breaking this whole process at this intermediate code. Now, if you look at the intermediate code, the beauty of the intermediate code is it is neither dependent on the source language, it is not dependent on the target language. It is independent of both. And actually, which is the beauty of the design as we go through, we will see, is when the intermediate code finally has some 8-9 different types of words, and that's all. No matter what programming language you are translating from, no matter which target processor you are targeting to, these 8-9 types of words can represent any program whatsoever that you can. So the advantage is you write the compilers in two separate parts. One is from the source language to the intermediate code translation, which does not need to know what is the backend language, what is the target language. You write separate piece, each one piece for each backend processor, which does not need to know for which language the program is being translated from. And then you have translators of C onto intermediate code, C++ to intermediate code, Java to intermediate code. Similarly, you have translator from intermediate code to x86 64-bit, intermediate code to x86 32-bit, intermediate code to Mac. And now whatever language pair you need for source and target, you just put these two together at the intermediate code level and you have the compiler. So for m source languages and n target processors, you don't need to write m times n compilers. You just need to write m plus n parts of the compiler. And that's the basic advantage of separating out the front end and the back end issues. Now, naturally, between these two, a whole lot of information has to flow. And that is where we will see this small tiny piece that I'm showing here, the symbol table, which plays a role, which tells which symbol is what type, what size, what kind of dependencies and all of that, which gets generated and populated in the front end and gets extensively used and mapped in the back end, the final table from which all those address expressions get generated in the back end. And this overall is a phased front end back end separation of a compiler along with the symbol table. So I think I will stop here and check if there are a couple of closing questions. Otherwise, in terms of the phasing.
There was one question from Rohit Gunwal earlier. So he was asking about the number of temporary variables.
Yes. Sir, is compile time dependent. Yes, of course. I mean, it's somewhat, but it's the compiler finally is a very optimized code by itself. And the way you do is when you initially generate the code at the after the semantic analysis, you are very liberal with the number of temporary variables that you use. But very often you take to strategies so that you can start optimizing the number of temporary variables. So it's not difficult to have strategies where you will have kind of as many temporary variables as there are expressions, kind of, which is pretty optimized in that whole way. We'll see through all those details when we go. Does the intermediate code generator produces codes of a line that is unique for a given set of instruction? No, it may not be. It may not be unique. All that you need is semantically equivalent. And that has catch. That has catch. I mean, as we'll see through. I mean, if everything was uniquely translatable, then things would not have been different between for the same language and the same target processor. The interpretation, I mean, all compilers would have strictly behaved in the same way, but it does not, because there are several places where such differences could happen. But typically, the intermediate code is a safe component, so it tries to keep the semantics to the best extent possible. When we discuss the intermediate code generation, then we'll talk about places where you may need a little bit of additional care to make sure that you get a unique semantics, though may not be in terms of unique set of instructions. Semantics need to be unique. Instructions need not be unique. Okay. Yes, Maitri Ranade, please. Go ahead, ask the question.
Sir, actually, I had a question about my initial query that you posted in the chat. Sir, the problem with using NAS is we won't be able to see the GCC compiler only generates the GNU assembly, right?
Right.
It won't generate NAS. So what should we do? Should we only use the GNU assembler, but it's not completely documented?
ISG, would like to take that question?
C means you can run GCC with -s or -w option and see what kind of assembly language is generated.
Actually, there is no way I was able to find to get my GCC to generate the NASM from the C code. So from the C code, it will only generate the GNU assembly, and there are some good resources about the GNU.
The assembly instructions are the same. They are not different. The only thing that are different are the assembler directives. Okay. The machine instructions are not different.
Also different, but the NASM uses the AT&T syntax, and the other one uses, I think, the Intel syntax. So, like, there's also a syntax difference.
Yes, there's a slight syntax difference. You should stick to whatever.
It's not slight, like they are not convertible as such.
So I think it is better to stick to the convention which GCC is generating.
And I actually needed some resources to learn about it, and I'm not able to find them.
You see, GCC, if you just read some materials on GCC will give you the detailed documentation about the assembly language that it generates. Okay. So we can share some links with you later.
Kindly please share links. So we should keep GNU our standard, because the existing compiler, they use GNU assembler only, right? So like.
Okay, in that case, ISG, in that case, I think it will be good if we can give them some pointers.
Yes. I can just share some pointers with them. Yes.
Yeah, actually, that's what happens. I don't remember when I last saw any assembler documentation, because it's, I mean, kind of feels intuitive. You read the code and you know what's happening. But I can understand that those who are getting started are having to refer to detailed manuals. So let's dig out something and give them. It is pass on that.
Okay, sure.
So I'll take that question of Ramnivas. How does intermediate code writes an if statement? Intermediate code, I just talked about the assignment type of intermediate code. There are control codes also. There is jump, there is conditional jump and stuff like that. For example, intermediate code is saying it is 3 address. Right. So for if, I mean that's pretty doable because you need 3 addresses to write an if. One address of the expression, the Boolean expression, based on whose outcome you will do the jump, and 2 addresses are the true and false targets. So 3 addresses again, which describes a if-else statement. So intermediate code actually has 3 address statements which use 3 addresses to represent a conditional jump with true and false target. We'll come to those when we do the details. This was just to give you an overview of what happens at different stages. Okay, Ram, I hope that answers your question. Is there any other question or doubt, anything?
Doesn't look like.
I think there's nothing else, right? Okay. Okay, students. Then this is. If there are no other questions, so we'll hang up for now, and we will meet again on Monday at 11 as scheduled. And I'll start with the discussion of the. So this here we have talked about the overall flow, the different phases. So now module by module we'll do a phase each. So on Monday I'll start with the second module, which will be on lexical analysis, and subsequently the lexical analyzer generator. So the lexical analyzer generator. That's okay. Then we will disconnect, disperse. Have a nice weekend, and see you on Monday at 11. Bye.